In every lecture, these circles around these X are different, right?
Sorry?
In every lecture, the circles around the X are different.
I guess they are a little bit.
Like a secret code.
Well,
Help me, I am trapped.
I didn't notice that before. It's not of my deliberate doing. So can we start? Or?
I think so. So thank you again for coming. This is the cover lecture of Professor Mann. And as always, please ask any questions that you have in the moment. It's more fun when people ask questions.
Okay, thank you. So, at this session, I thought we would talk about more exotic phenomena that I mentioned briefly yesterday, and there are various papers where these are done, plus others where people have explored them in different contexts. Multiple re-entrant phase transitions, thermodynamic singularities, isolated critical points, superentropic black holes, van der Waals black holes, and superfluidity. I think so. What I want to do basically in this session is discuss these. Now, these phenomena are generally observed when you have higher curvature gravity and or hairy black holes. In other words, black holes coupled to scalars, and that's where these kinds of phenomena tend to be seen. So, I'm going to talk about something that I think is quite familiar to the South American, especially Chilean theoretical physics community, and that's Lovelock gravity, since a lot of very...
It's the Canadian theory.
It's Canadian theory, yes. Lovelock was a professor at the University of Waterloo, where I'm from, when this was done in the 1970s. But people in this part of the world have really done some very innovative things with this. So Lovelock gravity is a generalization of Einstein's theory in which every term in the Lagrangian is a topological invariant depending on the dimensionality. The Einstein tensor, you might think, or sorry, the Ricci scalar, you might think is not a topological invariant, but actually it is in two space-time dimensions. It is a total derivative in 1 + 1 dimensions, and so you cannot use it to get any field equations. And basically the idea of Lovelock gravity is to exploit that property in higher dimensions. So this is a topological invariant linear in the curvature in 2 dimensions. This is a topological invariant linear, or sorry, quadratic in the curvature in 2, 3, and 4 dimensions. But in 5, it becomes non-trivial. Just the way in 3 dimensions, this becomes non-trivial. And so on. And Lovelock discovered that you could get what at the time were only mathematically interesting generalizations of Einstein gravity, and then some 25 years later and onward, people thought maybe they are physically interesting generalizations. So the idea is you construct theories non-linear in the curvature, and you can obtain them by demanding that the field equations are always second-order differential equations in the metric functions. And then I believe the answer in any dimensionality will be one, however many Lovelock terms you can get up to the dimensionality that allows them to exist. And if you make things more nonlinear in the curvature, it will just be topological. So we know the construction of all these things. It's a lot more complicated once you go beyond quadratic. But you can write them as a sum, with each one having its own coupling constant. So alpha 0 would be like the cosmological constant or proportional to it. This would be related to Newton's constant, and this is related to what one might call the Gauss-Bonnet constant. And the individual kth term is given by K products of Riemann multiplied by this fully antisymmetric product of Kronecker deltas. Or if you don't like that, it's the product of the epsilon tensor with the upstairs indices and another one with the downstairs indices. But you can show that tensor can be written as this antisymmetric product of Kronecker deltas. So, just to be explicit, I'll write the simplest one. Delta ABCD by definition is delta AC delta BD minus delta AD delta BC. And so that would be the one that would give you the simplest one. You have 2 down, 2 up. So if you apply this to the Riemann tensor, you'll get the Ricci scalar. Okay, the dimensionality limits this sum, which is basically what I said a few minutes ago, that if you you can let this sum go as large as you like, but once K exceeds this inequality, the terms no longer contribute to the equations of motion. You just get topological, you just get terms that are total derivatives in that dimension, and there's no contribution. So there are 2 special cases of this, one of which we found is interesting for black hole chemistry, the other of which hasn't been explored that much. One is Chern-Simons gravity, where all of these couplings are related to one another by this combinatoric factor, and where P runs from 1 to n minus 1, which is d minus 1 over 2. The other, which will come out in black hole chemistry, is when the alpha coefficients are related to each other via this other combinatoric factor, where this K is that K, and for little k here is between this range, so alpha 1, k equals 1, alpha 7, k equals 7, and so on. And that is going to be important a bit later on. So, the equations of motion. So, the action is written here. If you take a variation of this action with respect to the metric, you get this generalization of Einstein's equations, where this Einstein-like tensor looks just like what I showed you in the Lagrangian, except the first 2 indices are not contracting anything. They are free indices. So if you take 1 power of the Riemann tensor, but only contract 2 of the indices with this structure, this is going to give you Einstein's tensor, the Einstein tensor. Okay? So, the reason why this is fun, from a theoretical physics viewpoint, excuse me, is that you can exactly solve these equations under the conditions of spherical symmetry. And you can actually go a bit beyond spherical symmetry to include fibered spaces and so on. But we learn a lot in physics from studying exact solutions, and fortunately we can learn what this is like here. And so the answer you get is this. In other words, what I'm saying is, if you insert this quantity, or this expression for the metric, into this general set of equations, you end up getting this equation here, where this term is referred to as the Lovelock polynomial. So you can see it's a polynomial in the metric function f. Kappa is a quantity that is -1, 0, or 1, depending on the constant curvature of this space. -1 means it's hyperbolic, like a saddle. +1, it's a spherical space, and 0 means it's planar. So this expression here, the actual field equation is a total derivative, so you can integrate it upward. This is the constant of the this comes from a constant of the motion in the equation, and I give the constant m because you can show this m is the actual mass you would calculate from a number of standard methods. This is given by integrating the Maxwellian stress energy, so that's the actual charge you would get. And I'm going to call this thing x of r because it's a bit of a mess to write it out. So This is now very straightforward. The solution to any Lovelock equation is given by finding the solution to this polynomial, which we can do up to quartic explicitly, and then afterward you can no longer do it explicitly, you can only do it implicitly. So in Gauss-Bonnet gravity, when capital K is 2, here's the answer, where this x is this big expression here. And this is alpha 1 hat, which is related to alpha 1 like so. Alpha 0 hat is like so. It's just easier to use the hat terms because then the answer comes out like this. Without it, I'd have all these other dimensional factors in there, which are a pain in the neck. So when, for example, alpha 2 goes to 0, suppose I say, oh, well, I don't want Gauss-Bonnet, I want Einstein, I'm going to set alpha 2 to 0. Well, if you choose the minus branch, then you can see that that will vanish, that will vanish, that will vanish, and this term will cancel this term. So you get 0 divided by 0. So if you expand this in powers of alpha 2 hat for the negative solution, you will recover the usual solution of Einstein gravity. So Lovelock gravity has, well, Gauss-Bonnet gravity has 2 branches of solutions. One branch reduces to the Einsteinian solution in the limit that the Gauss-Bonnet coupling goes small. The other one does not, and it's an alternate vacuum branch of the solution. And of course, it wouldn't be too hard to see that if I have a kth order polynomial, I will get k different branches, and one of them will reduce to Einstein, and the others will not. Okay, how many have seen Lovelock gravity before here, or used it? Some, not as many as I thought. Well, yeah. But. Okay, so what about the first law and the Smart formula? You can get this for these theories. Here's the action. It's the sum of Lovelock terms, and I'm going to put in that Born-Infeld Lagrangian that I talked about last time, just because it gives an extra term. So, using the same geometric arguments I showed you earlier in the week on Tuesday, these fully carry through for Lovelock gravity. And what you get when you do that is this expression for the first law. A small change in the mass of a black hole solution is surface gravity times the change in area, or T delta S, temperature delta entropy, plus V delta P, which comes from the alpha 0 term. But what these 3 people realize is all the other alpha coefficients could likewise be varied in principle, and you would end up getting a psi delta alpha k term. I'll tell you what this is in a minute. But these basically are conjugate potentials to the alpha constants, just the way the volume is a conjugate potential to the alpha 0 constant.
Why you don't buy the Newton constant?
Because you want one reference constant that does not change. Basically, that's in there. Really, delta m means delta gm if you do it in an orthodox way. So you end up getting gm is really the variable of interest.
But typically m depends on all these alpha, right? Depends on alpha naught, alpha 1, alpha 2.
You mean insofar as when you calculate it at large? Well, that depends on how you look at it, right? It's a constant of integration in the solution that in principle doesn't have to know about anything. If you solve for a black hole, you can write some in terms of the other, but what's primary here? Yeah.
But there are critical points in the theory, and for instance, the mass behavior in the solution depends on whether the point is critical or not.
Yes.
So if you move away from if you compute the mass from a not critical point, and you move away by variations of the constant, how is consistent? Because
well, you would have to examine that as a special case. But generically, this is what's going to happen. But you're right, that special cases have to be treated. I'm going to show you a couple of special cases. I'm not going to claim that every special case has been looked at, but that, I hope, is good news for some people here, because it means there are more physics papers to write. But you're right, that has to be examined as a special case. Then there's the rotation parameters, which basically I know of no rotating solutions to Lovelock gravity except when you have the planar case. It's an unsolved problem to do an analog of the Kerr solution in Lovelock. And then you have charge, of course. That's the first law. And I actually forgot, sorry, the B delta B term. I meant to write it in and I forgot, but I've got it in the SMAR formula. And you can show this follows as well from Eulerian scaling. Alpha 0 scales like 1 over length squared. Alpha 1 doesn't scale. Alpha 2 scales like length squared. Alpha 3 scales like length to the fourth, and so on. So this coefficient is determined by the scaling properties of alpha, which are in turn determined by the dimensionality of the different Lovelock terms in the Lagrangian. And what they showed is these geometric arguments fully carry through for these things. So psi is by definition di-m, di-alpha. Psi k is di-m, di-alpha k, up to these.
Do you think that the Lagrangian is second order in the derivatives?
No.
So in principle you can do with whatever...
That's right, you can, and we have, I don't think I'm going to talk about this in these lectures, but there are some interesting quasi-topological gravities, and there are some terms, well, do you guys want me to digress a bit, or do you want me to keep going? Who votes that I go this way a little bit?
I just want to know...
So maybe I'll answer later. There are, yes, you don't have to have it second order. That's not required.
Excuse me, can we ask something? Maybe I don't have right to ask because I was not in the first part of your mini course.
Go ahead.
But, if you take a smart formula, but
Yes.
you don't regard the alpha like parameters that you vary in the first law, will this sums up somehow with other terms so that finally you get formula
No.
without this?
No.
Why?
No.
Because if I take the action and I evaluate it on shell with boundary terms and everything, I get smart formula in different form, and it should be consistent.
Just a minute, I accidentally did something here. Coupled it. Is this loose power? No, it's okay. Here we go. Okay, I don't know what happened there. Just give me. So the answer is no. You can see this even in the simplest. Let me get this back up again. This thing isn't working. Just let me put it back in.
And then why? Because when you calculate
Well,
the energy,
in the first law, you're perfectly welcome to keep any delta equal to 0 that you want. But the SMAR formula requires all these terms. You can just show explicitly that if you... Let's see if that's better. There we go. Okay. You can show explicitly in the Schwarzschild anti-de Sitter solution, that if you don't have this term, then you won't get m equals
yes,
Tx.
I don't say that you raise this term, but pressure and volume are functions of some constants, and they sum up with other terms, because volume is proportional to R plus horizon.
Yeah, okay, but so maybe I don't understand the question.
No, is that what happens is that PV is proportional to PS.
Yes.
So what you get is a different coefficient.
Yes. So this is my
So
question.
it's the same. It's the same.
Yes, okay,
Yes.
so there are, all right, well, I did address that, I think, earlier. There are certain solutions in certain theories of gravity where it happens to be the case that this is proportional to that, in which case you get what I call, Neok Park and Wilson Brenner and I did this, we called it a reduced SMAR formula. But, so you will see SMAR formulas that don't have this term or these, and you get different coefficients. But in every solution we have seen, it's because the solution has special properties that make these things proportional. In general, they are not proportional, and so you have to have these terms. But there are special cases where they are.
So like, for instance, when it's not proportional?
Well, the cases where they're most commonly proportional is in planar black holes.
Okay.
But when they're non-planar, they're generally not proportional. I cannot say that every non-planar black hole doesn't have it. But generically speaking, if you've got a non-planar black hole, you're not going to get proportionality.
Okay.
But in a planar one, you commonly do. And in a lot of the ADS CFT literature, they quote SMAR formulas all over the place that have different coefficients here and nothing here. And that's what got me curious. And the reason why is because it contradicts Eulerian scaling. So that's why we looked at it, and what we discovered was that if you start off the way that I would contend you do here, then you discover these solutions have this special property and you recover their answers.
Okay, but now I'm confused. If you, for example, in case of Gauss-Bonnet, even a non-planar case,
Yes.
that means hyperbolic
Yes.
and spherical, if you just calculate free energy from the point of view of statistical relation, you have that action is free energy,
Yeah.
proportional,
Yeah.
and then you evaluate the action, and
Yeah.
you don't know what you vary, because you just evaluate the action and you calculate
Okay.
free energy, and then you will obtain, I don't know, everything without PV and alpha.
Well,
K.
you'll get F is, you should get free energy is beta M minus entropy, but that's not a SMAR formula.
Yes, this is like quantum statistical relation, but it has a similar form and different coefficients.
Well, I would not call that a SMAR formula. I would say that's the definition of free
I
energy.
call it quantum statistical relation. This is true, but anyway, I mean, it should be related to SMART formula just by the definition of, I don't know.
Well, when you
sometimes
work
should be
it through, you
proportional.
don't, well, what I would contend is when you work it through, you always find this. And then the free energy, either from the action or for other things, by definition is well, we do it as mass minus TS. You could maybe absorb a PV term into the definition of mass if you wanted, but the free energy is not, that's not a SMART formula. That's the amount of energy the system has available to do work.
It is not, but it is the same function. It is also function of mass is function of all those quantities
yes,
without
that's true.
some terms. In that sense, mathematically, it should be equivalent. That means that some terms must be proportional. I don't know how because I haven't studied that, but that's why I asked you.
Well, I mean, so if you're asking me, could I rewrite this in terms of free energy? The answer is obviously yes, because free energy is m times something, or m plus other stuff. So I could do that if I wanted to do that, but it doesn't come out as nicely from scaling. All I'm saying is that if you, the original SMAR formula was just this part here, or these two with the charge, when you had charge. What I'm saying is if you leave this out in Lovelock gravity, you will not satisfy it, and if you monkey around with the free energy, you might be able to get something that works. But what I would expect to happen, I mean, maybe it could be tried to see it, what I would expect to happen is that you would have to recover this kind of formula with these kinds of terms. Okay, so one of the things you need to be careful of in these Lovelock gravities is the entropy. It is not always positive because it is no longer proportional to the area. It is the sum over a set of terms, as is these Lovelock potentials, and the terms are these three here. So the A term is a generalization of the area. It's the integral of the k minus 1 Lovelock Lagrangian restricted to the horizon hypersurface times the root of the determinant of the metric, which I call sigma here, on the horizon hypersurface. So for k equals 1 Lovelock, L to the k minus 1 is constant, and you get the integral over the horizon area. But more generally, you get this. So the curvature of the horizon surface enters into the area formula and therefore into the entropy in Lovelock gravity, and this is not guaranteed to always be positive. The B terms here, I don't have any good intuition for. This B is not the B of the previous slide. That's an unfortunate choice of notation. Just a sec. But this is another term that comes about when you properly carry through the geometric arguments, and likewise, so does this one. This is a generalization, if you remember from before when I had the volume was divergent and I had to subtract the ADS part off, add and subtract. This is a generalization of that. Yeah?
I have the impression that B is equal to 0 in Chern-Simon bidimensions.
That may very well be the case. This is generic.
Okay.
So there may be cases where if you look at it, I mean, if this is 0, then of course this diverges, but you would have to probably deal with that as a special case, and my guess is you'll find that term is annihilated by something else. So when you have special cases with the alpha, you have to go backwards because some things have been divided out to get this kind of thing. So the Lovelock potentials are calculable in principle, and if you go back to this spherically symmetric solution, this is what you get for the answer, and we actually calculated for the first time. Do I have the reference here? Yeah. In this paper, this is the first time these potentials were explicitly calculated for the spherically symmetric solution. So there's the mass in terms of the horizon radius plus Q plus. This is a generalization of what you get for the Reissner-Nordstrom solution. Yeah.
Isn't that
Sorry?
Isn't that diversion?
Well, this is done after adding and subtracting that term that keeps the volume and all the other Lovelock potentials finite. So if you remember...
You have to realize the action.
Well, not if you do it the way we did it. So crudely speaking, the mass was given by this integral at infinity of this surface area times this quantity that depended on d by dt, and that was divergent, but we subtracted off the omega ADS term times lambda, or some coefficient that I forget, and the volume was given by the integral of infinity of ds of lambda omega, where this omega, I guess I should have AB, there's an AB here, there's an AB there, there's an AB there, there's an AB there, minus omega ADS, AB, and then plus the integral at the horizon of the same thing. So this is divergent, but this is finite. And when you go to Lovelock, that expression I had on the previous slide, you have a more general structure here that you subtract off that makes the volume and all the other Lovelock potentials finite. So that's been done here, but I've suppressed all that stuff because it's just tedious to go through. So this is what you get for the Lovelock potentials. This is, the volume is the zeroth Lovelock potential, or related to it by this factor here. So that's the good old volume, Euclidean volume of the black hole. So that still persists in Lovelock gravity. This is the electromagnetic potential. This is the entropy. This is the temperature. There's this polynomial d of r plus, which I've written out here, that also occurs. The equation of state looks like this. So remarkably enough, even though this is a complicated mess, if you look at it carefully, remember, you can explicitly compute this because the only place where the pressure actually appears is the alpha zero term. And the alpha zero term is here, but it's not there. So you actually still can invert this equation to compute the pressure as a function of temperature and R plus, which is really the volume, or, which is much easier, the specific volume. The specific volume is a constant times R plus. So this is a very complicated generalization of PV equals nRT. If you multiply both sides by R plus, you'll modify this a little bit and you'll get the generalization of PV equals nRT. So this is a complicated, non-ideal gas of black holes from Lovelock gravity. So the arithmetic is more complicated, but conceptually it's not that different. So let me talk about these funny things. This thermodynamic singularity is what happens when you get the derivative of the pressure with respect to the temperature going to 0 at some particular volume. And then what that means is that the isotherms, which are lines of constant temperature, cross over each other at a singularity.
When do you say that it's a gas of black holes?
Well, because PV equals nRT is an ideal gas. So I mean, I'm using that very loosely just to say that in Lovelock gravity, you've got PV equals T plus tons of corrections to this formula. Whether you believe that's a gas or a liquid or something is, you know, I don't want to say it is a gas. I'm just saying it would reduce to this under the right circumstances. That's all I meant. So what would happen is the isotherms will cross. I'll show you a picture. But if you remember in van der Waals, right, you've got this kind of behavior, which is subcritical, where you get a phase change, critical, and then above critical. But lines of constant temperature never cross. When you have a thermodynamic singularity, you get this kind of behavior here, where lines of constant temperature actually cross over each other. And that happens when this D function I showed you on the previous slide vanishes. And it is possible under certain circumstances for this to be true. In general, it doesn't happen, but you can adjust parameters so that sometimes it does, particularly when kappa is negative, in other words, for hyperbolic black holes. For spherical and planar, it doesn't happen, but for hyperbolic black holes, it does. Excuse me here, I've got to deal with this for a minute. So this is something we found in this paper, this rather strange structure that can occur. So I'm going to walk you through some of the basic properties of black hole Lovelock chemistry, or Lovelock black hole chemistry, I guess. So the first thing is, you get a lot of standard behavior. In fact, I didn't need to draw it. Here's standard van der Waals behavior, 5-dimensional Gauss-Bonnet gravity for spherical black holes. Nothing unusual, nothing different than what we saw for the charged case. You get a swallowtail here, so there's a large black hole, first order phase transition to a small black hole. This is the free energy, this is the temperature. Rescaled in units of their critical values. And you get this coexistence curve, or you get this 3-dimensional swallowtail structure, and the slices give you this kind of thing. So we've seen this before. So lots of Lovelock black holes just do this. But the fun parts, of course, are the exceptions where you have something different. So this is what the surface of pressure versus volume and temperature looks like for a neutral hyperbolic Lovelock black hole and an electrically charged one. And here is where you see this phenomenon of isotherms crossing, both in the neutral and in the charged cases. So you would get, for example, curves where this is like above criticality, this curve here is at criticality, and this curve here is below criticality and dips around like that. Now there is something else that occurs, though, for these holes that constrains you from this rather weird behavior there. And that is the fact that you have a maximal pressure. And if you're below that pressure, then the solution is asymptotically ADS. But if you're above that pressure, you can show that you no longer have asymptotic ADS solutions. In fact, the structure of the metric function is such that it doesn't get out to infinity. It forces the space to close back on itself and become compact. So there are really two qualitatively different solutions bounded by that line, and the same is true here for any charge. So in that sense, the only behavior these things really can have is down here.
So can you say, so this is like, what is the meaning of that? What is the asymptotic form of the metric? In that
Well, it's a metric that is not a space that goes out to infinity. It's like it closes back on itself. There's no asymptotic region. Eventually, if you went out far enough, you'd come back on yourself. R becomes the radial variable you can show becomes a compact coordinate if the pressure is too large.
You mean it's periodic?
Well, it's not periodic, but it's repeated. It's like a black hole well, it would be if you had the surface of a sphere, the black hole would be on part of the sphere.
In a pole.
Well, you could put it in a pole if you wanted.
So this means that the time is periodic?
No, it's just a space.
But if, do you know this, can you write down anything that you have in mind?
Well, it would be the Gauss-Bonnet thing I had before with kappa -1, when the pressure is bigger than this. It's not I can't remember the details now, but they're in the paper I have with Antonio and David.
Excuse me, but do you talk about this Laurel polynomial that you show, spherical and symmetrical? Because this is not, I cannot imagine convex.
No, what happens is that the square root becomes imaginary.
Square root, that's right.
So you can go from R
right.
to some specific value to just a given bench.
That's the problem. That's exactly
right.
That's exactly right. So, we didn't find much more than that in Gauss-Bonnet gravity. The nonlinearity of the curvature did something, but where it got really interesting was when we went to third order Lovelock, which very few people look at in detail. So here's the equation of state in general. We're going to cut it off for certain values of k in the dimension. But before doing that, there's a lot of constants here, and it's easier to rescale everything in units of the third order Lovelock couple, alpha 3. And in particular, this parameter alpha here is the dimensionless ratio of the Gauss-Bonnet coupling to the third order Lovelock coupling. The dimensions are different, which is why you need a square root there to get that dimensions. So what we find, I'm not going to go through all the algebra, the arithmetic, we find we get 5 different cases, depending on how big this parameter is here. So if this parameter is small, then we have one critical point, and that's normal van der Waals. But if this parameter is in between this range, we get 2 critical points and something called reverse van der Waals behavior. I'll show you what that is in a minute. If alpha is root 3, it's a very special case containing this isolated critical point. And then in case 4, we get an infinite coexistence line, and if we're above this, we get multiple re-entrant phase transitions and so on. So reverse van der Waals, that would be this case right here. So let's illustrate it for third order Lovelock in 7 dimensions. This is what you get. So let's just choose alpha to be this value. It's within this range, and here's all the parameters, so you don't have to memorize what they are. So if you look at cold temperatures, this is as you get colder, you get normal van der Waals behavior, right? You have below criticality, you get a first order phase transition from gas to liquid. Critical point, and then you get this place where you're above criticality. But what is very strange about this solution is that as you get hotter, you get another critical point, and then you get a first-order phase transition. So it would be as though you started with ice, warmed it up, got to the critical ice-water point, kept warming it up, and then you got ice again. It's like going from ice to water to ice. Go figure. But that is what these things will do. So that's why we call it reverse van der Waals. As you get hotter, you get two phases separating instead of colder. You get multiple reentrant phase transitions, which are given by this graph of the free energy versus pressure and temperature, but it's maybe easier to see it in this slice. So I'm going to take a slice through here somewhere and look at different temperatures. Now, the small black hole solution is this solid line. The large black hole solutions are these various dashed lines, depending on what you choose for the pressure. And I can get other small black hole lines too. I just put one of them in here so you can see what's going on. So suppose I start with the pressure equal to this value, let's call it P prime. And it's hot. The large black hole has less free energy than the small one, so I'm going to have a big black hole. As I cool it down, I will reach the first order phase transition, and then it will be a small black hole. But as I keep going, I reach a second kind of phase transition, where it then becomes large again. So that's what's meant by multiple reentrants. You get it once, and then you get it a second time, and we found you can get more than even that. Now, what about the isolated critical point? This is what happens when the reverse van der Waals first order transition exactly touches this critical point, as does the normal van der Waals first order transition. You can see all these things merge together. That happens for this one special value of alpha under these circumstances. And what we find now is a very new kind of black hole. In a normal thermodynamic black hole, if you power series expand the pressure near criticality, you get this expansion in the temperature, and from this you can read off the standard critical exponents. This is delta equals 3, for example. If you have to take derivatives to see that, and the gamma, this I think is, this linear in T is gamma equals 1, and so on. Yes?
So is this the maximal degeneracy case, or what? Or 3 parameters?
What do you mean by maximal degeneracy?
Is this Lovelock unit vacuum of maximal number?
To our knowledge, well, we looked at the geometric and other properties of this hole and found nothing unusual.
But what does it mean K equal to 3? K equal to
That's
3?
third order Lovelock. That's all that means. That's 7 dimensions, third order Lovelock, hyperbolic, and no charge.
All the vacua are different, or are all the vacua the same?
They're different. They're different.
Okay.
Yeah, this is the one that reduces to Einstein. Yeah, sorry. So in this case, that's the isolated critical point, and if you expand the pressure near criticality around there, then you find you get different terms. I'm missing the A term, for example. This term is not linear, it's quadratic, and you find that beta is now 1 instead of a half, and gamma is equal to 2. So this is the first example we've seen of a black hole, which is not a mean field theory black hole. It is actually something different. So the normal scaling relations are violated here, but they satisfy other things they should satisfy. So we took a look at these isolated critical points in this paper, and we found they're quite generic. If you let the Lovelock couplings be related to each other by this expression here, where A, this constant A, is related to the Lovelock cutoff, K was 3 in the example I showed, you could have K as big as you want, times the square root of this alpha parameter here. So in third order, when k is equal to, capital K is 3, then this alpha was the 1 over root 3 that or square root 3, sorry, that I showed you before. So what you end up getting is you get this kind of solution here from the Lovelock polynomial, and the equation of state takes on this special form. It's still linear in the temperature, but it's depends on the specific volume quite differently than the normal equation of state. And what we find is that when capital K is odd and kappa is negative, in other words, it's a hyperbolic black hole, you have two distinct first order phase transitions merging at a single point. And that gives you non-standard critical exponents. So here is the expansion of pressure about criticality for general kth order Lovelock, and you find these are the non-standard critical exponents. They care about K. When K was 3, gamma was 2, and delta was 3. But when K is 5, gamma is 4, and delta is 5. Beta is always 1, but not a half. So here is what I said. This is blue is normal, red is unusual. Now, this isolated critical point happens to be at the same place as the thermodynamic singularity. So we thought maybe this is just really weird thermodynamic behavior because of this thermodynamic singularity. But Hannah Dykar and Roby Hennegar and I found in this paper that's cut off at the bottom, and Jay just this year, this is not a necessary condition. You can have isolated critical points that have no thermodynamic singularity. So that's just a peculiarity of the particular solution we happen to look at. In general, this does not happen. It doesn't have to happen. So here is what's going on from the viewpoint of coexistence. This is normal van der Waals behavior, right? You have a large black hole, a small black hole, you have a gas, you have a liquid, they have a critical point, and this is the boundary of the first order phase transition. When you have reverse van der Waals, you've got a large region and a small region where you've got first order here, but at hot temperatures, you've got another first order here. They each end in their own critical points. So in this zone here, you can't distinguish gas from liquid. So it's like you had water. I used ice and water, but I probably should have done this. You have water. You have steam. You cool it down and you get water. But then you have steam and you heat it up and you get water. Very strange. When you have an isolated critical point, these two points merge right there. And it's there where you get the unusual critical exponents. If you go above this value of alpha, then this critical point no longer is a second order transition and it's smooth again, and you get sort of like this behavior. Except it goes on, there's no critical point anymore, so it goes on forever. So what was gas liquid becomes liquid solid, basically. So what about this weird thing? Well, there's a thing in condensed matter physics called the Witten relation that all critical exponents are supposed to satisfy, and that's true for these black holes, so there's nothing screwball about that. There is the Rushbrook inequality, that's also satisfied. So there are general theories of how critical exponents are supposed to behave, and these black holes with these unusual exponents are still satisfying. The Ehrenfest relations are satisfied, and there's something called the Prigogine-Dufay ratio. That's a ratio of certain parameters, critical parameters in a phase transition. It's basically beta divided by delta. And this suggests a kind of liquid glass phase transition. So maybe these are, I'll show you in a minute, maybe these are glassy black holes. We found this in Lovelock, but to answer an earlier question that I can't remember who asked it, quasi-topological black holes that are not always second order also exhibit the same kind of phenomenon. So, if you look, this is a graph of the Prigogine-Dufay ratio for a whole bunch of different kinds of polymers and alloys and glasses and all this stuff. These black holes have a Prigogine-Dufay ratio 1/K, which means it's less than 1, and there are certain substances, whatever they are, polyisobutane and polysulfone, and I don't know what to do with these things, but maybe these black holes are polymers or glasses of some kind. And what we do with this, further science, remains to be undetermined. But to get back to what I said early on, if you believe quantum gravity should describe thermodynamic behavior of black holes, then it darn well better tell us about this, because this is not going away. So here's the summary. You have reverse van der Waals behavior, you can have a thermodynamic singularity, you can have an isolated critical point, and this is, you can have multiple reentrant things where the entropy is positive here, positive there, but a no man's zone or no person zone in the middle where S is negative. There's more to explore here, but nonlinear curvature introduces very different behavior than Einstein gravity. Yes?
I will use the notation of your one of your paper with Castor, that you were calling Lovelock unique vacuum.
Oh yeah, the love, yeah, that was a while back.
And let's say in Lovelock with 3 curvatures, let's say in 7 dimensions, there is the maximal degeneracy condition, that is Chern-Simons, but there is something in between, like this Einstein-Gauss-Bonnet, let's say, with a. So what is the qualitative different behavior between these two?
Thermodynamically?
Yeah.
I don't know, because we haven't explored it in detail, so I can't answer that. That's yet another problem for an enterprising grad students to look at. We haven't looked at that case.
Because, okay, maybe...
We probably should. In retrospect, I should have, but there's only so much to do for a unit time, and as we find one thing, but you're right, it's a good question. I don't know how to
Because, I mean, from the... Maybe it had nothing to do, but the theories with maximal degeneracy had a completely holographic description. I can give you details later.
I didn't know that. That's where, yeah, that's I see. Yeah, that would be, yeah. So you can find
I mean, in a single sentence, usually the anomaly, the bile anomaly in an odd dimensional asymptotically anti-Sitter gravity have the type A anomaly and type B anomaly. In Chern-Simons, there is only type A anomaly. So it's sort of weird dual description, not unitary or something like that. So I think no one had ever studied the situation in between. That's the reason why I was giving the 7-dimensional example between that there is this quadratic curvature gravity theory that no one knows what type of holographic description it has.
Yeah. So we have not done this. It's a very good question. It's worth doing. I didn't appreciate that other point you said. So that's, yeah, we just didn't do it.
Right.
Okay. Superentropic black holes, which we learned about and wrote up in this paper. Let's go back to something less exotic, Einstein gravity with the Kerr-Newman anti-de Sitter black hole, and it's charged, so that's the Q, there's the potential. And now you can do something that's rather interesting with this black hole. You can rescale the azimuthal coordinate by this quantity here, 1 minus a squared over L squared. Then take the limit everywhere in the metric that a becomes L, which will make this thing diverge, be an infinite coordinate. But then you just tell the metric, no, that's a compact coordinate. You still get an exact solution to the Einstein equations with this metric, with these parameters. In fact, we didn't discover this. Clem did, but by a very different method. What we did was show this was generic. He had a rather obscure way of going about it, and we thought when we understood its connection to the original Kerr metric, then we realized this was very generalizable. So, what the heck is this? This is a black hole whose event horizon looks like this, if you embed it. So if I take the event horizon of a black hole and ask what would it look like if I embedded the surface in 3 space dimensions, I get a sphere. If it's a black string, I get this. But these guys look like that, where this goes up forever and down forever. This is a new ultra-spinning limit to the Kerr class of metrics that people had not looked at before. People looked at other limits where A goes to L, but not this particular one for some reason. And what you find is the event horizon becomes non-compact. It's like a Lobachevsky space, if you know what that is. Does anybody know this cartoon by M.C. Escher? You know, the guy who likes to have stairways go around. How many have heard of M.C. Escher? You know, these pictures? Some of you haven't, really?
I think they don't recognize the name. Yes, but they
I
have
should
always
say
seen
this.
this.
If you add the contrary, nobody will answer us.
Sorry?
If you add the contrary, nobody will answer. So you have to ask, all of you know Esper, right? And then,
Escher.
Does this make now you recognize this? Yeah, you know, the stairways that go around like this and like this, and you know, people walking down these stairs forever and they never get anywhere. He has a diagram called Angels and Demons, where the angels and demons get smaller and smaller as you go out. Well, that's a pictorial representation of a Lobachevsky space, and that's exactly what this is. It's Lobachevsky at the top, it's Lobachevsky at the bottom, which means if you were a bug on the horizon at the equator, the North Pole is infinitely far away from it. It's infinite proper distance away, and the South Pole. In fact, the North and South Pole are infinite proper distances from any other point on the horizon. So it's not compact, but the area is finite, because these taper off so rapidly that although the poles are infinitely far away, the amount of area is finite. They're asymptotically anti-de Sitter, but the boundary is rotating at the speed of light. And we found, what we found was curious about this is these were the first counterexamples to this reverse isoparametric inequality that I told you about last time. So that's why we call them super entropic. They have more entropy than they should have given their volume. The reverse well, let me just go on and talk about that more. So here is this super entropic black hole metric. These are the parameters with mass, angular momentum, angular velocity at the horizon, temperature, entropy, electric potential, and charge. There is this new parameter mu that has to do with the compactification scale of psi. That's a new physical parameter of the theory. And so you get an addition to the first law that we've already seen, where this K parameter is like the conjugate of the chemical potential, which is what mu is. The reason why we called it that is there's a body of literature about things called Schrödinger black holes, which also have, you describe them in a coordinate that's partly null, but as you go to infinity, the null coordinate becomes periodic. So this is the other way around. This is a periodic coordinate that at infinity becomes null. So its physical variable, we thought, well, they call it chemical potential, we'll call it chemical potential. So what are the basic properties of these crazy things? They have both extremal and non-extremal solutions. The extremal values are when this equality is satisfied. So m naught is the extremal mass. They have no closed time-like curves, so even though this azimuthal coordinate goes null, you can show there are no closed time-like curves in the space-time. This quantity here is the, what is that thing? Oh, it's G psi psi. That's what this is. It's positive outside the horizon everywhere. The horizon is not compact. That's the metric on the horizon. And you can see this coordinate kappa, which is L times 1 minus cos theta. This is, if you absorb this and make it exponential, you've got an exponential factor on the azimuthal part. And as you go to the north or south poles, kappa goes to plus or minus infinity. Yeah.
Excuse me, if all these superentropy black holes take some kind of similar geometry of each other,
Similar what?
Kind of similar geometry, like this one, will be something like their safety correspondence?
Well, I'll get to that. Just wait. Yes, I mean, that's an interesting question. We have some information on that. They have an ergosphere, and what is most interesting for black hole chemistry is they violate this inequality. So what the conjecture was of Gibbons and collaborators is that this thing was always greater than or equal to 1, and it was equal to 1 when you were at Schwarzschild anti-de Sitter. When you had Kerr, it was bigger than 1. So that told me that the interpretation was, if you give me a thermodynamic volume, I want to know what area the black hole has that maximizes the entropy. And the answer is when R is equal to 1, and you get Schwarzschild ADS. Well, here you find that this is less than 1, so by the same reasoning, if you give me a volume, thermodynamic volume, then these black holes have more entropy than they are allowed to do. A is bigger, which makes this smaller. And this is what it explicitly looks like for the uncharged case. You can see this is clearly less than 1 for all values of the horizon. That's why we call it that. So what's the asymptotic structure of these things? Well, David Kubiznak pushed us to be skeptical and said, oh, maybe this is just some weird coordinate thing. You chose a special kind of coordinates. Well, the answer is no. We found that you could actually redefine the rotating coordinates in a one-parameter family, and if you compactify something else, you still get this. In other words, all choices of the rotating frame yield the same limit if you do this. It's not a special choice of rotating frame. The conformal boundary is ADS3, the azimuthal coordinate becomes null. But if you go to the conformal boundary, you find it's perfectly normal ADS3, just described with a null coordinate. And that is the boundary metric right there. Well, what about higher dimensions? The answer is yes, these crazy things occur in any dimensionality. You play exactly the same game with the azimuthal coordinate. So here is higher dimensional curve, but with just one rotation. And that's what the superentropic thing would look like. It just has this stuff going along for the ride. So there it is again. And here are the thermodynamic parameters. And we found that it had all the same basic properties. The reverse isoperimetric ratio gets this exponent instead of 1/6. But other than that, it's really not very, very different. So the next thing we looked at is, well, what if you have two rotations with charge? And the only solution I know of that has that is this solution right here. Excuse me. So we had, we took this Chong et al. Solution, which is an exact solution for a doubly rotating charged black hole in gauge supergravity. And so it's a very complicated metric that has all of these functions here that feed into these parameters. It's a very complicated thing that you're not going to absorb this just by a slide. I'm putting it in here so you know we did our homework. But what you can do is take one of the azimuthal coordinates, let's say phi, and redefine it like so. Take the other one and redefine it like so, and then rescale this guy by the chi-a factor. Remember, chi-a looks like that, 1 minus a squared over L squared. Let a go to L, and then compactify the new thing, and you get a superentropic, doubly rotating, charged black hole. And now the event horizon, when embedded, has this onion kind of structure, but it gets fatter as the other rotation gets larger. And you might think, well, this is great fun. Let's now do the same thing for B that we did for A, but the answer is you can't. And we found this to be generic. You can only do the superentropic case once. You can do it for any rotating coordinate you like, but once you've done it, the other limits all become singular. And we tried really hard to get doubly superentropic. You can't do it. We could find no way of doing that.
But in certain dimensions, you have also one superentropic or two superentropic?
Just one in any dimension, anything. We could not do it for any multiply rotating black hole. When you do this once, the problem is the second time you'll get a metric singularity in one of the polar coordinates, and you can't get rid of it. You can't do it by redefining. We found no way of doing it, so I should back off a bit. I can't say there is absolutely no way of doing it, but I can say we worked mighty hard to find it and could not find a way. So I am skeptical that it is possible. So, the thermodynamics of this supergravity, superentropic black hole, here's all the parameters. It's complicated. And then you get this volume. Now, I can't look at that and say, oh, that's going to violate the reverse isoparametric inequality. Maybe you can, but I'm not that smart. So we actually had to explicitly compute it, and we found that it's not always superentropic. So this red surface is the boundary where the isoparametric parameter is 1. If you're above 1, you're in the normal zone. If you're below 1, you violate it. So the blue curve is the actual value of R. This R is the blue sheet as a function. So for 0 charge, this is this quantity plotted versus R plus over L and B over L. So this is the extra rotation, this is the horizon size. So there is a superentropic region. Likewise, if we fix the value of the horizon size and plot R versus charge and rotation, again, there's a superentropic region. But there's also a non-superentropic region. Here, the reverse isoparametric inequality is obeyed. So it's a bit of an unfortunate name because these superentropic black holes are not always superentropic. But I like the name, so we're sort of going to keep it. So a superentropic black hole is a class of black holes that can violate the reverse isoparametric inequality under certain circumstances, but they may not always do so. Okay, and what's going on, as you can see, is the more orthogonal spin you have, the more the effect is. Likewise, the bigger the horizon, the more the effect is.
Is there any limit where there is no ecosphere of this?
Not that we found. All right, I'll have one slide on van der Waals black holes. This is something we tried to play with, but it sort of didn't go anywhere, but it's a bit instructive. I have shown you up to now van der Waals-like equations. They have qualitatively the same behavior, but they're not the real thing. So we thought, let's reverse engineer it. What would a black hole have to look like so that its equation of state exactly looked like that? It was real van der Waals. Well, the answer is you can get it, but you've got to put a spherical black hole inside a distribution of exotic matter. In other words, matter that violates the energy conditions. And so here's an example. This is where the event horizon would be. This orange curve is the energy density. This red curve is the energy density plus the pressure. This is the pressure. So you can see, oops, what did I do now? Don't send them anything. It's a terrible thing to send. Sorry about this. Go. So what we found is you get this case where you can see here the energy density goes negative at a certain region outside the horizon, and this asymptotes to a constant. So you've got an inner zone that's perfectly fine, but you've got an outer zone where you have exotic matter. We couldn't find any way to get out of this. We tried, but it didn't work. So if you want the real van der Waals equation, you're going to have exotic matter, or maybe some exotic theory of gravity. This is Einstein.
A negative rho is like a cosmological constant.
Well, but it's extra matter, and it's also not constant. So you can't have it constant. That won't work. It's got to have this kind of distribution here.
And rho plus p is never zero?
No, it's beyond that, and it violates P. So right here you can see both the weak and the strong energy conditions are violated. So here it's fine.
But the null is satisfied.
Sorry?
The null energy condition is okay.
I think so.
Yeah, the strong
Yeah. All right, so one of the very recent things we found and published this year were black holes that are like superfluids. Superfluid helium in these two papers here. So a superfluid phase transition is a line of second order phase transitions. Up till now, every second order transition I showed you happened at one point in parameter space, a critical point. This is a critical line. It's called a lambda line for reasons that will become clear in a minute if you haven't heard of it. So what we found is that we got a line of second order phase transitions separating the normal black hole from what we call the superfluid one, only because this is second order. Here's helium-4 in the real world, and here's this line of second order transition here between normal helium-4 and superfluid helium-4. You know, superfluids, you put them in a jar, they crawl out, they're like some animal that you can't control. So the slope is different, but qualitatively it's exactly the same. So we found this in a context of theories that I think some people in this room are familiar with, some of the authors. These conformally hairy black holes, which are basically Lovelock gravity with a charge if you want. Actually, we needed the charge. Lovelock gravity with charge, but also with this product of curvatures here. So they're all contracted together with this extended Kronecker delta, but this S tensor is given by this structure here. Very complicated. It couples a scalar field to curvature with these derivative terms, and you might ask, why on earth would anybody ever do anything so complicated? Well, the reason is that, I thought I put them on, maybe I didn't. You can show that this entire Lagrangian, or action, is locally conformally invariant. If you conformally rescale the metric and the scalar field, this is conformally invariant. And that's what interested these people here. So
this is just the Lovelock Lagrangian conformally transformed. Yeah, you introduce a field such that when you change the field.
No, but it's not transformed because it's invariant. So if I conformally transform Lovelock, it'll be cancelled by that.
You take Lovelock, you transform it, you say G is equal to
Yes.
phi squared G bar.
Yes, yes.
But now, if you transform phi squared and G bar, G will be invariant, you see?
Okay, in that sense, yes. Okay. So what these guys found is that if you put in spherical symmetry, then the Lovelock polynomial equation becomes just like I showed you earlier this morning, except you get this extra term, which is the Hare parameter due to the scalar. So the scalar goes like a constant divided by R. It's finite everywhere except at the origin, but that's where the space-time is singular anyway. The Hare parameter is given by this linear combination of constants beta k, these funny things depending on dimension, and little k, and this constant n right here, depending on how many of these you have. So it cares about these coupling constants beta, this constant of integration n, and kappa is the curvature parameter here.
So what is this in 4 dimensions?
Well, just put in d equals 4. It works. K equals 1. So, here's the Lovelock polynomial. It turns out you have to put constraints on the coupling constants and the constant of integration for this to be a solution. But as long as you have at least 3 terms, you can always solve these equations. There's no obstruction to doing that. So here's the Lovelock thermodynamic parameters with the modification in red due to the hair.
So it doesn't exist in 4 dimensions?
That's right, it doesn't. Yeah. And D is this polynomial. So now let's do that rescaling game. This should be alpha 2 over alpha 3. Sorry about that, not alpha 3. It should be alpha 2 over alpha 3. That's a typo. The equation of state now looks like what we got in Lovelock, but with this extra term. And this power of D matters a lot. Notice the sign is negative. So when you solve the critical equations, you find that they have a degeneracy when h and q squared have these particular values, when alpha is root 5/3 and when the critical volume becomes 15. And then you find the critical pressure is no longer a single point. Rather, you get an equation between the critical pressure and the critical temperature. That's the line of second-order phase transitions.
Nice.
That's what superfluid helium does. That's what superfluid black holes do. For all critical temperatures, you have infinitely many critical points in a line. So, this is why it's called a lambda transition. If you plot the specific heat of superfluid helium as a function of temperature, the data go sharply peak and go like that, and somebody thought this looks a bit like the Greek letter lambda, so we'll call it a lambda transition. That's what the black hole does. This is the line of second order phase. Here's superfluid helium. And this is what the free energy does. At all these critical temperatures, you get this same second order phase transition. Now, you don't just need conformally coupled Lovelock or conformally hairy Lovelock black holes. We found it in cubic, Hannah, Roby, and I found this in cubic quasi-topological gravity as well. This tends to be normative in black hole chemistry. Once you find some phenomenon in one place, you often find it in other places in other theories. It's quite common. The first time is the hardest time to find it, but once you found it, then you know what to look for and where to look, and it makes it easier. So that's it for this morning. I hope I've convinced you that there's a lot of fun stuff in black hole chemistry besides a lot of normal chemistry. And I guess what I'll talk about, am I out of time now? I guess. Got 10 minutes.
10 minutes.
Yeah. So I'm going to stop here. This is my last slide for this morning. So we can take questions or discussion if you like. What I'll do in the final session is tell you about what I think some of the frontier areas of this subject is. And so I'll come back for the last one. And, any questions?
So let's thank Prof again.